By the late 1980s, every major railway system on Earth had scrapped its steam fleet. Every system except one. While the rest of the world melted down its engines, China was still building brand new steam locomotives at the Datong works, and then quietly sealing some of them inside underground bunkers. Not as museum pieces, not as memorials. These machines were greased, dehumidified, and held on turning schedules in hardened storage. They were kept ready for a day China hoped would never come. A rising superpower, preserving its most obsolete technology underground. The obvious question is why? But the real answer lies not in the past these engines came from, but in the future they were built to survive. In the modern rail age, steam traction is an active operational liability. A steam engine demands massive volumes of coal, constant stops for water, and relentless, labor-intensive upkeep. It is dirty, thermally inefficient, and obsolete. By every measure of industrial progress, these steel giants represented a step backward for a nation rapidly modernizing. The logical path was to melt them down, reclaiming thousands of tons of high-grade steel to build the factories and bridges of a rising power. Instead, keeping these machines functional was a live, ongoing choice. It required a continuous commitment of resources, maintenance crews, and specialized facilities that otherwise would have supported modern diesel and electric fleets. This was a deliberate rejection of standard economic efficiency in favor of absolute redundancy. The preservation of these engines exposes the constant tension between rapid development and long-term survivability. Instead of being treated as delicate historical artifacts, these machines remained heavy-haul tools of crisis, kept in working order at immense state expense. Retaining obsolete locomotives is highly wasteful during peacetime, but their value changes entirely if the modern energy grid fails. The decision to preserve this heavy machinery shows a strategic calculation. When modern systems are vulnerable to disruption, the most primitive, self-contained technology becomes the most reliable fallback. By the late 20th century, global rail networks had shifted. North America and Europe had retired their active steam fleets decades earlier, fully committing to diesel and electric power. To Western observers, coal-fired locomotives belonged in museums or scrapyards. Yet across some of the vast networks of China, steam engines remained the undisputed backbone of national transport. This was not a slow transition or a localized oversight. While other nations dismantled their steam infrastructure, Chinese factories continued to mass-produce heavy, coal-fired locomotives, keeping assembly lines active at a scale unseen anywhere else on Earth. This persistence was a national industrial pattern woven directly into the state's broader economic planning. China's immense geography and expanding industrial base demanded a transportation network capable of moving millions of tons of raw materials across thousands of miles. Instead of racing to match Western technological timelines, state planners leaned into a system they could fully build, fuel, and maintain using entirely domestic resources. The decision established the country as the world's final massive stronghold of steam power, laying the foundation for a resilient logistics network designed to survive external disruptions. The sheer scale of this ongoing steam network anchored an industrial system that defied global trends, turning a supposedly obsolete technology into a central asset of the state. At the center of this industrial effort stood the Datong Locomotive Works in Shanxi Province. Established as the nation's premier heavy locomotive facility, Datong carried the manufacture of mainline steam traction late into the 20th century. While factories across Europe and North America had long since retooled for diesel and electric propulsion, Datong spent the decades between 1964 and 1988 mass-producing the QJ-class steam engine. This massive 210-2 locomotive, designed specifically for heavy-haul coal transport, became the primary output of an assembly line operating with high industrial precision. This was not a localized repair operation or a slow winding down of an obsolete technology. It was a massive, state-supported manufacturing system characterized by disciplined organizational continuity. Production at the Shanxi facility rose steadily through the 1970s, reaching its peak in 1980 when the factory rolled out 325 brand-new QJ-class locomotives in a single year, nearly one completed engine every 27 hours. Thousands of boilermakers, machinists, and engineers worked in synchronized shifts, forging heavy frames and casting cylinders on a scale unmatched anywhere else in the world. By the time the final QJ locomotive rolled off the erecting shop floor in December 1988, the total production run of the class had reached 4,717 units. This late-era manufacturing timeline serves as clear evidence of a durable, standardized industrial network. Every locomotive featured identical parts, from the high-pressure boilers to the mechanical stokers, ensuring that the nationwide fleet shared a single, reliable supply chain for maintenance and engineering support. Datong did not merely keep old engines running, it built a vast, standardized transport fleet from the ground up, establishing a logistics network designed for long-term operational durability. The engine designated to lead this standardized fleet was the QJ class, short for Qian-Jin, meaning advance. Designed specifically for heavy mainline freight, this locomotive represented the summit of China's domestic steam technology. It served as a highly functional industrial tool built for grueling, sustained labor across the national rail network. At the core of the QJ design was a 210 two-wheel arrangement, placing 5 coupled driving axles on the tracks to ensure heavy physical traction on steep mountain grades. This configuration delivered the massive adhesive weight required to prevent wheel slip while hauling heavy mineral trains. To withstand the immense internal pressures of continuous operation, Datong built the locomotive with a strong, fully welded boiler. Reliable daily operations relied on mechanical stokers that automatically fed coal into the firebox, alongside air-operated rocker grates that cleared heavy ash with pneumatic power. Large 12-wheel tenders carrying 35 cubic meters of water and 22 tons of coal ensured these machines ran long distances without frequent stops. These design choices translated directly into immense working capability. The QJ generated roughly 33,000 kilograms force of tractive effort, allowing a single locomotive to haul thousands of tons of bulk cargo at a design speed of 80 kilometers per hour. This performance profile matched the exact operational needs of the country's heavy-haul industrial corridors, where moving massive payloads reliably over vast distances took priority over speed. Every mechanical component was built for long-term durability and straightforward field maintenance, ensuring that basic railway workshops could service the engine using standard hand tools. This simplicity and sheer physical strength secured the QJ's role as the definitive workhorse of the Chinese industrial transport network. A modern diesel or electric locomotive is a complex network of electrical relays, high-pressure fuel lines, and integrated circuits. When one of these components fails, the entire machine halts, requiring specialized diagnostic systems and imported replacement parts. Steam traction operates on an entirely different mechanical principle, relying on raw physical forces rather than delicate technology. Every critical assembly on a QJ-class locomotive is exposed and physically legible. A cracked rod, a leaking boiler tube, or a worn brass bearing is immediately visible to the human eye. There are no digital black boxes or proprietary software codes blocking access. A local railway workshop, equipped with basic lathes, forging hammers, and welding tools, can fabricate replacement parts from raw steel stock on site. This mechanical simplicity shifts maintenance from a high-tech supply chain issue to a local task. A machinist can patch a boiler plate or repack a piston gland using standard tools. If a boiler tube ruptures, a work crew can plug it temporarily to keep the engine moving, avoiding the need for a custom-engineered computer chip from a foreign supplier. Under highly constrained conditions, this structural transparency becomes an important advantage. The physical nature of the machine allows basic hands-on repair skills to replace advanced technical training. A steam locomotive operates independently of global electronics manufacturers. Its survival depends entirely on the physical strength of steel, the heat of a local fire, and the practical expertise of the workers standing beside it. China's prolonged reliance on steam traction was anchored in a simple geological reality. The country possessed some of the largest coal reserves on Earth. This abundant resource formed the absolute backbone of the national energy supply, accounting for nearly 70% of primary energy consumption throughout the late 20th century. While other nations faced severe energy crises and volatile oil markets, China stood on a virtually inexhaustible supply of cheap fuel. Unlike diesel, which required complex refining and relied on vulnerable transport networks, raw coal could be mined, moved, and burned using simple, existing technologies. This fuel advantage matched the challenges of a massive rail geography. As the state pushed its rail lines far into remote interior regions, it encountered rugged terrain, extreme climates, and vast distances. Supporting modern diesel or electric locomotives in these outer territories required an immense, expensive infrastructure footprint. A diesel fleet demanded a constant supply of refined oil, specialized fuel tankers, and secure storage depots spread across thousands of miles. Electrification was even more capital-intensive, requiring high-voltage transmission lines, heavy electrical substations, and a regional power grid of absolute stability, capabilities the developing nation could not yet deploy at scale. Steam locomotives bypassed these logistical barriers. As self-contained power plants, they required nothing more than raw coal, water, and basic mechanical attention to operate. They could run reliably in sub-zero temperatures and high altitudes where delicate electronic systems often failed. This physical utility directly refutes the common Western caricature of China's steam network as a relic of industrial backwardness or ideological stagnation. The decision to keep these coal-fired engines running was a highly rational economic choice. By using steam to move bulk freight and mineral trains through the interior, state planners preserved scarce petroleum reserves for high-priority sectors like military aviation, agriculture, and modern chemical industries. Retaining the steam fleet allowed the nation to modernize its busiest mainline corridors at a measured, sustainable pace, preventing a costly over-reliance on advanced foreign technology and ensuring that the transport network remained grounded in domestic physical realities. In peacetime, the heavy-haul steam locomotive is an economic liability, demanding massive tonnage of fuel and constant water stops. But during a national crisis, this inefficiency undergoes a complete strategic inversion. A diesel locomotive is entirely dependent on a vulnerable supply chain, requiring refined petroleum, functioning pipelines, and secure storage depots. An electric locomotive is even more fragile, bound to a centralized power grid that can be disabled by a kinetic strike or a cyber attack. If those modern networks fail, a nation's logistical spine paralyzes. A coal-burning steam fleet bypasses these systemic vulnerabilities. China's decision to preserve its standardized QJ locomotives was a direct hedge against this exact failure point. By 1993, China had transitioned into a net oil importer, exposing its transport sector to foreign embargoes and maritime blockades. Coal, however, remained an abundant domestic certainty, fueling nearly 70% of the nation's primary energy. A steam locomotive is a self-contained power plant. It operates without refined fuel, electrical transmission lines, or advanced microchips. It runs on raw coal dug directly from local mines. In a total grid collapse or an oil blockade, these machines could step in to transport troops, heavy armor, and raw materials across the interior. Keeping them ready was a hardened insurance policy. The preservation of these locomotives represents an active contingency plan for national survival, ensuring that the country's transport network could continue functioning when modern technology was stripped away. The rumor of a hidden network of steam locomotives transitioned from speculation to documented record through a specialized locomotive register. Compiled between October 2006 and early 2007, this registry tracked equipment at the Jinju 701 Rolling Stock and Locomotive Factory, a secure military-grade workshop built within a mountain valley in Liaoning Province. Within these files, 3 specific QJ-class locomotives, serial numbers 6998, 7002, and 7040, were officially marked with a 3-letter designation, STR, standing for Strategic Reserve. These units were managed directly by the Railway Research and Development Center, a state-controlled entity. This official classification provides the most concrete paper trail supporting the existence of a state-sanctioned reserve. However, the limits of this evidence require careful interpretation. While the STR designation aligns with Cold War contingency programs used in Europe and the Soviet Union, no formal Ministry of Railways policy memo or central party directive has ever been made public. The available files do not show a vast, subterranean fleet of thousands of engines waiting to be mobilized. Instead, the documentation indicates a much smaller, highly targeted contingency program. The physical evidence at Jinzhou 701 suggests that the state maintained a limited, experimental reserve of standardized heavy-haul engines, keeping them mechanically preserved inside a hardened facility. This targeted insurance policy stood in place of a massive hidden army, proving that while the scale of the bunker rumor was exaggerated, the strategic intent was entirely real. In military and railway logistics, sealed storage is an active, demanding engineering process. To keep a 100-ton steam locomotive ready for rapid deployment, mechanics had to combat a relentless and silent enemy, moisture. In a humid mountain tunnel, uncontrolled dampness would render a locomotive useless in a matter of years. According to standard preservation protocols, such as those in Chapter 11 of the historical manual, Steam Locomotive Construction and Maintenance, sealing an engine required a strict, multi-step sequence. First, crews drained the boiler completely, flushing the interior with dry air to prevent rust from eating away at the high-pressure steel. They coated every moving part, from the valve gear to the axle boxes, in thick, humidity-resistant grease. But the most difficult challenge was preventing the physical distortion of the machinery under its own massive weight. If a locomotive sits idle for months, the heavy axles can flatten the brass bearings underneath them. To prevent this, maintenance rules required strict turning schedules, where crews periodically rotated the driving wheels to redistribute oil and keep the bearings round. The state's military logistics manuals mandated a similar level of care, prescribing a regular cycle of lubrication and component checks. This disciplined routine reveals that the underground chambers were active workshops rather than passive vaults. Sealing was distinct from abandoning a machine in a dark cave. It required a constant program of dehumidification, ventilation, and physical inspection. The objective was immediate readiness, not historical display. Every locomotive was treated as a functional reserve kept in a state of suspended animation through constant manual labor. At the Datong Locomotive Works, the pressure to produce went beyond meeting standard industrial quotas. A retired shop foreman recalled that as late-stage assembly continued into the 1980s, specific engines were pulled aside under strict state protocols. Mechanics finished these units and immediately prepared them for long-term suspension. The instructions came directly from military-adjacent administrative channels, bypassing commercial rail authorities. Workers filled grease cups with heavy, high-grade tallow, sealed critical piping with oil-soaked canvas, and applied protective asphaltic compounds to the exposed running gear before the locomotives ever turned a wheel in revenue service. In the depots of Liaoning and Inner Mongolia, The responsibility of keeping these engines ready fell to local railway engineers. Dated log entries from facilities like Jinzhou 701 outline a highly disciplined maintenance cycle. Every 90 days, stored locomotives underwent a mandatory inspection. A retired depot manager described the rigid authorization chains that governed these assets. These engines remained under the dual oversight of the Ministry of Railways and regional military logistics bureaus. Moving or modifying an STR-designated locomotive required direct clearance from national mobilization authorities. The logbooks show a constant battle against moisture. Teams conducted regular hydrostatic boiler tests and used hand pumps to circulate protective oils through the internal cylinders, preventing the heavy steel boilers from weakening due to internal rust. The practical value of this technology during a crisis lies in its mechanical simplicity, a reality demonstrated by modern restoration mechanics. Repairing a modern diesel locomotive's fuel injection system requires high-tolerance electronic calibration tools and clean room facilities. In contrast, a steam crew can repair a leaking superheater element or a blown cylinder packing gland in the field using a heavy sledgehammer, a hand chisel, and a portable forge. If a boiler tube ruptures during a national emergency, a work crew can drive a tapered steel plug into both ends of the damaged tube. This action isolates the leak, allows the boiler to hold pressure, and returns the train to service in under an hour. This direct, low-tech serviceability ensured the transport network would not depend on specialized foreign electronics or complex supply lines. When American preservationists acquired surviving QJ locomotives, including units 6,988 and 7,081, from China in 2006, the physical state of the machines revealed the effectiveness of this preservation system. Mechanics who stripped down the imported engines found that despite years of outdoor exposure, the internal cylinders, piston valves, and boiler plates remained free of deep scaling and corrosion. The grease applied during their storage had hardened into a protective shell, preserving the original machining marks on the steel rods. This pristine metal proved the effectiveness of a professional, state-directed mothballing program designed to keep heavy machinery in a state of suspended readiness. From a defense logistics perspective, keeping these machines viable was a highly practical choice. An operational analyst explained how these steam assets would function during a foreign oil embargo or a total power grid failure. If an adversary severed coastal shipping lanes, cutting off diesel imports, or launched a coordinated strike that disabled the high-voltage electrical grid, the nation's transport network would instantly freeze. In this scenario, the strategic reserve would deploy. The rail network could draw upon local, low-grade coal deposits, bypassing the paralyzed electric grid and the dried-up fuel pipelines. The steam fleet would serve as a heavy-haul fallback, moving coal, raw materials, military divisions, and heavy armor across rugged mountain passes that modern diesel and electric traction could no longer cross. It was a redundant system built on the physical certainty of coal, water, and steel. The strategic reserve of steam engines functioned as a direct branch of the Third Front, a massive defense mobilization program launched in 1964 to prepare the country for military invasion. Under this policy, state planners systematically relocated heavy industries and logistical hubs from vulnerable coastal regions far into the rugged interior of the country. The core directive of the Third Front was simple: disperse critical facilities, hide them in remote mountain ranges, and build inside protective caves. This policy of strategic depth became an urgent national priority following the 1969 border clashes with the Soviet Union along Zhenbao Island. Confronted with the threat of a sudden, high-intensity conflict against a superior industrial adversary, Chinese military planners prioritized survivability over peacetime efficiency. Every component of the nation's transport network had to operate independently of centralized infrastructure. In this climate of immediate external threat, the steam locomotive became an essential asset of national survival. If foreign strikes deactivated the electric grid or severed oil pipelines, these coal-fueled machines that would run on local resources to keep supply lines open. They were built and maintained to ensure transport survived, even if the modern economy collapsed. The silent engines inside these mountain bunkers were the ultimate expression of this doctrine. They are relics of a past age preserved as a fallback for a feared future. The National Rail Network retired mainline steam in 2002, but the actual end of active commercial steam in China was a slow, uneven fade. On the Jining Tongliao, or Datong, railway in Inner Mongolia, massive QJ locomotives continued to haul heavy freight across rugged mountain passes. This joint provincial venture kept mainline steam active long after the rest of the country modernized, running double-headed QJs in regular revenue service until December 2005. For local operators, it was a practical choice, keeping reliable, low-cost assets running where coal was cheap and the necessary water stops were already built. Once the mainline tracks cleared, the remaining operational engines retreated into isolated, specialized industrial pockets. Steel mills, chemical plants, and open-pit coal mines across the northern provinces relied on older traction like the SY and JS classes for heavy switching and short-haul duties. These machines quietly extended the life of steam in regions where upgrading to modern fleets was too expensive. The final regular steam chapter unfolded at the Sandaoling open-pit coal mine in Hami, Xinjiang. In this remote western desert, a fleet of industrial locomotives spent decades hauling coal from the pit floor up to the processing plants. Sandaoling outlived every other active commercial steam operation on Earth. The final regular steam-powered coal trains ran in April 2022, and the last operational locomotives officially retired on January 14, 2024. This slow public demise represents the natural end of steam as a commercial tool. It was an entirely separate path from the silent, heavily maintained machines kept in strategic reserves. While the active fleet slowly wore down to its final bolts in the deserts of Xinjiang, the preserved units remained suspended in time, clean, oiled, and waiting in the dark. Today, the physical remnants of China's steam era exist in sharply contrasting states. More than 80 QJ-class locomotives survive on static display in museums and parks, including prototype units 0001 and 0004 in Beijing. Others remain in forgotten industrial yards, slowly rusting in the open air. A handful found a different fate abroad, purchased by American collectors who restored units like 6988 and 7081 to working order for regional heritage runs. But beyond these documented survivors, the trail disappears into speculation. Persistent reports of pristine locomotives still sealed inside secure mountain bunkers continue to circulate. To date, no concrete physical evidence, photographs, or official records have emerged to verify the existence of any remaining underground caches. What remains is a strict division between the verified and the rumored. The confirmed record leaves only a scattered collection of silent monuments and a few overseas restorations, while the actual fate of any hidden reserves remains unproven, locked away in classified state archives. Today, our hyper-connected world relies on vulnerable digital grids, but deep underground, these silent machines reveal a different philosophy. True resilience is analog. This hidden reserve is not a relic of the past, but a warning for the future. It shows how far a nation will go to survive the unimaginable. When the modern grid fails, what remains? Share your thoughts in the comments below.